Students, welcome to our physics channel, Physics Star. Today I am going to explain the topic waves, and I have done previously 5 videos based on waves and up to speed of a transverse wave in a string. I have done the videos. Please go through my previous videos and come to this video so that you can have a continuation, right? So now let us discuss about the continuation of the topic, that is energy density of a transverse wave. So let us discuss about that. What is meant by energy density of a transverse wave? Here, energy density of a transverse wave. So how to discuss this energy density of a transverse wave? Now let us say what type of energy is that a stretched string have, like suppose if a string is there, now we are just giving a certain bump to it so that the wave will be generated, the pulse will be generated, and the pulse will be moving throughout that length of the rope continuously. Am I right or not? That is what we call progressive wave, right? And we are discussing about that progressive transverse wave here. Okay, now let us suppose if a wave is there which is created, okay, if a wave is there which is created in a string or a rope, okay, now in this, once if the wave is generated, automatically it travels with a certain velocity, and we know that velocity formula also, v is equal to root of t by mu. We have calculated that, where mu is the linear mass density of the string, right? Now let us discuss how to find the energy possessed by this wave. Usually it will have two energies. What are they? That is potential energy as well as kinetic energy. How to understand the potential energy here? Where is the potential energy here? Actually, if we observe this carefully, then consider one element in this total rope. Total rope. Now let us assume one element. This is an element. Now I am taking an element here, and on this element, if it is traveling, already we discussed while we are deriving that speed of wave in a string, we discussed that on this part of the wave or on that part of that string, there are two forces which are acting on both sides. That is, in this direction the tensional force will be acting, and in this direction also the tensional force will be acting. And we have calculated we have taken the components of tensional forces. Because of that, okay, now we have derived the velocity equation also. Am I right or not? So there are two tensional forces which are acting on that particular element dl. Okay, so on this element there are two forces. Because of these two forces, there might be some elongation in the string. Am I right or not? Because every object, if each and every object, due to certain force, definitely there might be some elongation. Am I right or not? Elongation or compression, right? Even here also the same thing we can observe in the rope. Due to the two tensional forces which are acting on both the sides, automatically the string will expand to some extent. Am I right or not? That because of that expansion, and that expansion leads to certain potential energy in the string. Okay, once again I am repeating, because of tensional forces which are acting on both the sides of element of string. Okay, see here there are two tensions are acting, right? Because of these two tensions, there will be some elongation in the string. There will be a slight elongation in the string, and because of that elongation, certain potential energy will be developed in the string, and we are going to find out that potential energy now. Okay, so let us find that potential energy. See here, I am not going to take at this situation, but I am going to consider the wave at a the part of the wave or the part of the rope at this situation, at these 2 points. See here, at these 2 points I am considering the wave. Now observe carefully. This is the part of the wave which I am considering with red color I have drawn, right? Now, because of the tensional forces, it is elongated. Usually before this it was flat. Am I right or not? Before it is generated, before a pulse is generated, it was flat actually. Rope is kept on a horizontal surface. It was flat. Okay. So it means that if this is a length L, then definitely we can say that this length will be greater than this one. Am I right or not? So we can write it as L plus DL here. Am I right or not? L plus DL we can write, where DL is the elongation. Yes or no? As the wave is propagating through that, there a certain elongation it has got. Okay na? Now about that elongation we are going to discuss. Okay, consider this distance is dx and this distance is dy. Okay, there you got a right angle triangle. Observe here carefully. You got a right angle triangle here. If we take a smallest elementary portion of it, we are going to get a right angle triangle or not. So that right angle triangle I am going to draw here separately. See here. Now let us assume that this is a right angle triangle. Let's take that part of that. Now here this is, consider it is a dx and it is dy. Assume that this is dl. Let us assume this is dl only. The length elongation, let us assume that elongation is dl only. Let us assume like that. Okay, consider it is dl. Okay, so that in that dl length, in the dl elongation, we can say, let us apply Pythagoras theorem here. As it is a right angle triangle, we can apply Pythagoras theorem, right? So we can write that dl whole square is equal to dx whole square plus dy whole square. Okay, therefore dl is equal to root over dx whole square plus dy whole square. We have got dl value. Now, how to find the elongation in the string? How to find the elongation? Initially it was dx. When it was flat, the length is a dx now. When it was flat. But now it has got increment in length and that's why it became dl. So, elongation, we can write it as elongation in the string due to the propagation of wave. Elongation in the string due to the propagation of wave, we can write dl minus dx. dl minus dx. Do you understand? So it is dl minus dx. Now, how to write this dl minus dx elongation? Dl minus dx is equal to, what is dl here? Root of dx square plus dy square. Now what am I doing? I am taking dx square as common so that it comes out of that root and I will get dx into, okay, root of, this time taking dx square as common in that. Okay, so dx into root of 1 plus dou y by, let us write it as partial differentiation because wave is represented in two variables. Equation of a wave is represented in two variables. That's why while we are differentiating either with respect to x or with respect to t, we need to take only partial differentiation. Okay, so 1 plus dou y by dou square, dou x square, 1 plus dou y by dx whole square is minus dx. Do you understand this? First dl value I have taken, in that root of dx whole square plus dy whole square. In that I am taking dx square as common, so that I am going to get 1 plus dou y by dou x whole square. Okay now. So dx square is getting common, right? So root of dx square is what? Dx. That's why I have taken dx as common completely. So now let us discuss about this. Dx is taken common in two terms, so that 1 plus dou y by dou x whole square and whole power 1 by 2, because it has square root, right? Minus 1. Now dx into 1 plus 1 by 2, because these are all very very smaller values. That's why I can apply binomial theorem. So because of that, I can take the two terms, first two terms of it, that is 1 plus power is there, no, 1 by 2, that, so multiply the second term dou y by dou x whole square with 1 by 2. That is how to expand according to binomial theorem. This is how we have to expand. 1 plus 1 by 2 into dou y by dou x whole square minus 1. Therefore here 1 gets cancelled. Hence what am I going to get? Half into dx into dou y by dou x whole square. Half into dx into dou y by dou x whole square. This is what we have got. This is what? Elongation in the string, dl minus dx, elongation in the string. Because of what? Why elongation has happened here? Because of propagation of wave through the string. Okay, and because of this elongation, it has got some potential energy, it possesses some potential energy. Now let us write that potential energy equation here. Therefore potential energy potential energy of element, potential energy of that element, dm, I have taken that potential energy as a du, because smallest element, it gains only smallest potential energy. Am I right? That smallest gain in potential energy, that is du. So du is equal to, how to write that du? Because of tensional force, that elongation is happening. That's why force into displacement. Am I right or not? Force into displacement. Force is tensional force. Tensional force into displacement. Therefore, T into what is dl by dl minus dx, that is half into dx into dou y by dou x whole square. This is du, and this is a potential energy element for gained by the elementary portion of this entire rope. Okay, in that du, let us write it clearly, half into T into dx into dou y by dou x whole square. Here let us write what is dou y by dou x. Y is equal to, let us write the wave equation here. Y is equal to a sine, consider it is kx minus omega t. Y is equal to a sine kx minus omega t. See, some people are getting confused. Okay, now between the y is equal to a sine kx minus omega t, y is equal to a sine omega t minus kx. About all those details, if you want, just go to my previous lectures so that you can understand it very easily. Now I am going to take it directly, y is equal to a sine kx minus omega t. If you want a clear cut explanation why we are taking, what is the meaning of a sine kx minus omega t, or what is the meaning of a sine omega t minus kx, then just watch my previous lectures. Okay, now let us take this y is equal to a sin kx minus omega t. In this, let us write dou y by dou x. Let us write dou y by dou x, so that I am going to get what? Sine becomes cos. So, and here x value k is there. Am I right or not? If we differentiate that, k will come outside, so that finally I am going to get k into a into cos kx minus omega t. Differentiation is important. Dou y by dou x. We are taking partial differentiation. See here. When do we consider partial differentiation? When there are two variables. More than one variable is there in a function, in a given function. Y is equal to a sin kx minus omega t is a function. It consists of two variables. One is x and the other one is t. Now if you want to differentiate the entire function with respect to only x, not with respect to t, then what I have to do? I need to take partial differentiation. Meanwhile, t has to be taken with, if we are doing it partial differentiation with respect to x, it means that t remains constant. We are making at a particular instant of time. Okay, now at a particular instant of time, like taking a photograph and observing that entire wave pattern. Okay, so at a particular time, if we are observing, then t remains constant. At that time, if you want to differentiate the total function, y function, therefore we are going to get dou y by dou x, partial differentiation. So dou y by dou x is equal to ka into cos kx minus omega t. Now let us write that dou y by dou x value in this equation, that is half into t into dx into dou y by dou x is what? Dou y by dou x whole square is what? K square a square cos square kx minus omega t. Kx minus omega t. That is du. That is du. And we know here half into, okay, let us write that in terms of speed of wave. V is equal to, in the previous lecture I explained about the speed of wave. V is equal to root of t by mu. Okay, therefore v square is equal to t by mu. Therefore, how to write this t value? Mu into v square. Now let us substitute the t value here. Mu into v square into k square into a square into cos square kx minus omega t dx. Let us write the dx last. So what is k square a square, or what is v square k square here? V omega is equal to, or else let us write v is equal to speed of a wave formula. One more formula is there for a speed of a wave. V is equal to omega by k. There is one more formula for speed of wave. I have explained this in previous video. Please go through it. V is equal to omega by k. Okay. So V is equal to omega by k. So instead of that, if we are writing V into k, instead of that we can write omega, right? So V into k, V square into k square, I can write omega square a square cos square kx minus omega t dx. Now if we want to find the average value of that potential energy which which a string gains, if you want to find the average value means for one wave, how much average potential energy that the string gains. If we want to calculate that, then we are going to integrate, or simply we can take the average value as du is equal to half into, either we can integrating that cos square kx minus omega t dx with respect to x, we are integrating, and finally for x values let us substitute the limits as 0 to lambda, because for one complete wave we are saying, no, so that's why from 0 to lambda we have to apply the limits. Apart from that, now what am I saying? I am just saying how to consider average value of cos square kx minus omega t. For any cos square value, not only this one, this is dx. For cos square kx minus omega t, and the limits are from 0 to lambda, now we are going to get the average value of this cos square omega t minus kx minus omega t is nothing but 1 by 2. Average value. Remember that half into mu omega square a square into average value of it is what? 0 to lambda. If we substitute, we are going to get 1 by 2. 1 by 2 into dx. Now, therefore, du by dx. What is du by dx? Let me write it clearly. Du by dx means potential energy. Therefore, potential energy per unit length of the string potential energy per unit length of the string is du by dx is equal to half mu, half, it's not half, it is 1 by 4, right? 1 by 4 mu omega square a square, okay, that's it, 1 by 4 mu omega square a square. This is the potential energy per unit length, du by dx. Do you understand? Potential energy per unit length. Per unit length, if you are taking, means what does it mean? It is energy density only, no? Energy per unit length. Okay, it is energy density only. That's why I am taking du by dx is equal to half mu omega square a square. We have got. Okay. Now let us discuss about kinetic energy. Kinetic energy means what? Not the entire wave's kinetic energy. I am not discussing about that. I am just taking an element of it and I am finding out the average kinetic energy of that string, or average kinetic energy of a wave which is produced in a string. Now let us discuss about that kinetic energy of a transverse wave. So now let us discuss that kinetic energy as a dk here. Which one? That element that I have taken in the previous one, right? See this one. For this one I am taking dk value. Dk is equal to dk is equal to half into dm into, because mass of it is half mv square, no? Half into dm into v square. What is v here? Speed of a wave. Half m into v. Half m into v square, right? Now let us write the dm value here. Half into dm value is what? Mu into, actually we have to write lambda, but lambda means in waves we may get confused, right? Lambda means we may understand that it is wavelength, misunderstanding, right? That's the reason why I am taking a separate term, that is mu here. Mu into dx, that is mu is what? Density into length, that I am going to get it as dm now. So mu into dx into v square. Therefore half into mu into dx into, we can write, instead of v square I can write what? Omega square. Let us write first what d square means what. First let us write that, because you may not understand this. Now instead of v square, what am I going to write? See, observe carefully. Dou y by dou t whole square. Dou y by dou t whole square. V is that only, no? So therefore, what y is equal to a sine kx minus omega t. This is a wave equation that we have taken. Now, if we differentiate this with respect to time, we are going to get the speed of wave. So dou y by dou t is nothing but the speed of wave, that is omega a cos kx minus omega t. Observe here. Actually, we will get minus here, but we are going to take square of it, right? So therefore, dou y by dou t can be written as omega square a square cos square kx minus omega t. Now let us simplify this. Half into mu into, consider it as dE by dx from now. Send this dx to left side. Half mu omega square a square into taking the average value of cos square kx minus omega t. So I can get now half into mu omega square a square into average value of it is 1 by 2. Therefore, I am going to get what? Half mu omega square a square. This is what? dE by dx. I'm sorry, dk. I'm sorry. It's dk. Kinetic energy, right? dk by dx. dk by dx. So we have got the dk by dx. Again, this is also the same we have got. Observe this carefully. Same equation we have got. Whatever the equation of du by dx, the same is the equation of dk by dx also. Am I right or not? What does it mean? It means that, okay, potential energy and kinetic energy throughout the progressive wave, throughout the transverse wave in the string, potential energy and kinetic energy values, okay, do not change at all. Potential energy, how much amount of potential energy is there, the same amount of kinetic energy also there. But in SHM it is not like that. Have you observed once? In simple harmonic motion it is not like that. It depends on distance. Am I right? As a particle is moving to certain distance, its potential energy and kinetic energy, okay, will not be same. Only at a particular point they will be same, but not all the times. But here it is not like that. In case of waves, throughout the propagation of progressive wave, transverse progressive wave, kinetic energy and potential energy, what we call energy density, kinetic energy density and potential energy density, both are quite same. Understand? There is no change in kinetic energy or there is no change in the potential energy as long as the wave is propagating. Okay, so therefore now let us discuss about total energy of wave. Total energy of wave. Total energy, it is total energy density of a wave. Total energy density of a wave. Now let us discuss about total energy density. What is total energy? This is dE by dx is equal to du by dx plus dk by dx. Du by dx plus dk by dx. So let us add both of them. 1 by 4 into mu omega square a square plus 1 by 4 into mu omega square a square. Therefore, what am I going to get? Half mu omega square a square. This is dE by dx. This is a total energy density. Total energy density. You need to remember it. dE by dx is half mu omega square a square. Whereas kinetic energy or potential energy, we are going to get 1 by 4, not half. Okay, dE by dx is equal to half mu omega square a square. This is a average energy density of transverse wave in a string. Okay. So this is also constant, right? Total energy also remains constant. Half mu omega square a square, right? So for one wave, if you want to write, let us write here. For one wave, if you want to find the energy density of one wave which is propagating, then we can write dE is equal to, send the dx to that side, half into mu omega square a square into this dx value is there, no? That I am going to write as, see here, half mu omega square a square into lambda, where lambda is wavelength. The dx value, maximum value of dx is what? Lambda only, right? Lambda. So that is the energy. E is equal to half mu omega square a square into lambda. This is energy of the total wave in a string. Got my point on it? Now let us discuss about power of the wave. Power of a transverse wave. Let us discuss about that. So observe these formulas once. Okay. Now I am going to explain power of a transverse wave. About power of a transverse wave, if we want to discuss. Now power P is equal to what? Energy by time. Energy by time. Yes or no? Let us write that energy by time here. How to write? That is half into usually energy value, let us write this in instantaneous values. So dE by dt. Now I am going to write it as simply dE by dx into, dE by dx into dx by dt. Can I write like this? So therefore V into dE by dx I can write. Am I right or not? Very simple. We need to multiply the total dE by dx value with V. That's it. Therefore dE by dx is equal to half into mu omega square a square into V. This is power. This is power here. So power at that instant of time, this is instantaneous power. Power at that instant of time, we can write it as half into mu omega square a square V. Okay now, half mu omega square a square V. This is a power formula. Okay. Now let's find intensity also. Let us find the intensity of a wave. Now intensity of a wave, intensity of a transverse wave in a string, intensity of a transverse wave in a string. Now let us see what is intensity here. Power per unit area or energy per unit time per unit area is called as intensity, right? So I can be written as power per unit area. Area, if I write A, you may confuse that area A is a cross section of that string. You may confuse. That's why I am writing it as S. What is S here? Power per unit area, right? So therefore I am writing power is equal to, power P is equal to half mu by S into omega square a square into V. Sorry, you may confuse that, it's not area of cross section. If I write it as A, you may confuse that it is amplitude. I'm sorry. S is area of cross section. If I write it as A, area of cross section as A, then here also one A is there. This A is amplitude actually. So you can write half into mu by S is equal to rho. Rho is what? Mass by volume. Rho is equal to mass by volume, density. Okay now, mass density. Rho means mass by volume. Volume means what? Volume of wire. Wire will be in a form of cylinder, right? That is area of cross section into length. Area of cross section into length. And if you want to write it as take this as dm because very small, right? That's why take this as dm by s into dx. What is dm by dx? Lambda only, no? Sorry, mu by s. Therefore, instead of mu by s, I am writing rho into omega square a square into v. This is I here. This is I. Okay, what is I here? Intensity of transverse wave in a string. Half rho omega square a square v. Observe this carefully. Half rho omega square a square v. And there are different types of waves, right? There are spherical waves, there are plane progressive waves. Okay now, suppose if there are spherical waves, for spherical waves, okay now, for spherical waves, I is equal to, usually how to write in terms of power? I is equal to power into area. Am I right or not? Power into area of cross section. Power into area of cross section. Yes or no? So power into, if it is a spherical wave front, not in string, I am not saying in strings. If there are some spherical wave fronts, spherical waves, then we can write P into 4 pi r square. Am I right or not? What is the surface of it? What is that area of that? 4 pi r square. Therefore, I is proportional to r square. About spherical waves. Do you understand? I is proportional to r square. So this is about energy density. Means in that, let us listen from the beginning. Energy density of a transverse wave. In that I have explained about potential energy and potential energy per unit length, what that is 1 by 4 mu omega square a square. Okay, and again I have also calculated kinetic energy of a transverse wave, that is dk is equal to, and dk by dx is equal to 1 by 4 mu omega square a square. And finally we understood that both kinetic energy density as well as potential energy density are equal as long as the wave is being propagated in the string. Okay, hence the total energy of a wave, now I have calculated it as half mu omega square a square. Hence the power of a transverse wave is half mu omega square a square v. And finally intensity of a transverse wave, half rho omega square a square v. This is intensity. So this is about energy density of a transverse wave as well as power and intensity. Now in the next class we will discuss about some problems. We will discuss how to solve the problems based on these. Okay, thank you very much, and please like, share and subscribe to my channel. Thank you.